I am M. Yogita from CSM. Here I am going to explain about apply the concept of B plus trees to optimize data retrieval in the database management system. First, to apply the concept of B plus trees, we know about the B plus trees. Introduction to B plus trees, where B plus trees are self-balancing tree data structure. They stored data in a node form in their nodes, and they maintain stored data and allow for efficient insertion, deletion, and such operations. B plus trees are widely used in database management system for optimizing data retrieval. It is very easy to optimize data. It is very easy to retrieve the data in the B plus trees. Here it is an example of B plus trees and structure of B plus trees. B plus trees consist of internal nodes and leaf nodes, where leaf nodes are the last nodes and dead nodes are. Internal nodes store keys and pointers to chain nodes, while leaf nodes store the actual records. Where where the where these two are internal nodes and these are all leaf nodes, where internal nodes store keys or pointers to chain nodes. All leaf nodes are linked, allowing efficient range queries. Well, some methods to optimize data retrieval: choosing the appropriate attribute for indexing. Identify the columns that are frequently queried or searched. First, we have to identify the query which is frequently used. For example, in a database, frequently receives queries like select star from orders where order date between 2023-01-01 and 2023-01-31. It would be beneficial to create a B plus tree index on the order date column. For example, in an order table, select orders from between the dates 2023-01-01 to 2023-01D. It is a query which is frequently used. It would be very beneficial to create an index or to create a B plus tree based on the order date. Analyze the query that involve range searches or lookups based on a key to determine which columns would benefit most from indexing. Creating B plus tree based index. Create primary and secondary indexes on the identified columns using a B plus tree structure. To identify B plus tree structure, we have to use primary and secondary indexing. Most modern relational dbms like MySQL, PostgreSQL, and Oracle automatically use B plus trees as the default structure for indexes, whereas Oracle, MySQL, PostgreSQL automatically used B plus tree structure for indexes. In SQL, you can create an index with a simple command. In a SQL, we have to use create index idx order date on orders or of order date to create an index. The dbms internally uses a B plus tree structure to store and manage this index. While the dbms internally uses B plus tree structures to store data and manage this index. Each node of the B plus tree will hold keys. In this case, the order date values and pointers to the corresponding records to the table. Whereas whereas each node in the B plus trees hold keys and pointers to the corresponding records in the data table. Using composite or multi-level indexes. If queries involves multiple conditions like searching by customer ID and order date, some queries are there with involve multiple conditions that time we use using composite or multi-level indexes. Creating composite indexes can be effective. A composite index with B plus tree allows you to efficiently search by both keys. B plus tree allows efficiency while creating composite index or multi-level indexes. Create index IDX underscore customer underscore order on orders of customer ID comma order date. The P plus trees will store these keys together and traversing it will help retrieve records faster. Where uh, where B plus trees allows these both keys, whereas customer ID and order date, and it traverses data faster and to give an output. Optimizing range queries. Range queries. Example, fetching all orders between 2 days benefit from the sequentially linked leaf nodes in a B plus tree. When a range query is executed, the dbms can traverse the leaf nodes of the B plus tree without needing to go back to the internal nodes repeatedly. Where range queries fetching all orders between 2 dates linked with the leaf node in a B plus tree. When a range query is executed, uh, dbms directly in the dbms they can directly traverse the leaf nodes without go back to internal nodes repeatedly. This minimizes the cost of retrieval also. uh, execution time is also less. For example, select star from orders where order date between 2023-01-01 and 2023-01-31. The above query will use the B plus tree index to quickly find the starting point and then continue scanning the leaf nodes sequentially until it reaches at the end point 2023-01-31, minimizing this input output with high fan out. The B plus trees high branching factor. The B plus trees have high branching factor ensures that each node contains a large number of keys, reducing the overall tree height. Uh, the reducing overall tree height to data retrieval. The database's disk pages or blocks can store more keys, decreasing the number of disk accesses needed to find the desired record. This is especially useful when dealing with large data sets, whereas B plus T is very useful when we handled large large amount of data sets. It can store multiple keys and more keys to optimize data retrieval. This is especially where reducing the number of disk access leads to significant performance gains. Whereas implementing clustered and non-clustered indexes. Clustered indexes where the data stored according to the index. Clustered index means where the data stored is according to indexes key, one by key to key, that and are often implemented using B plus Ds. This ensures that when a record is accessed, its adjacent records are likely to be on the same page or nearby pages, leading to fewer disk seeks. In constant, non-cluster index, where the index holds pointers to the data, where the index holds pointer to the data is known as non-clustered index, are also implemented using B plus trees. Whereas non-clustered index are also implemented using B plus tree. Non-clustered indexes are useful when you create multiple indexes on different columns of the same table. Non-clustered data is used when we use multiple indexes on different columns of the same table. For example, we have in the same table and different columns. We use multiple indexes. That time we use non-clustered data. Whereas index maintenance and updates. A B plus tree index is automatically maintained by the dbms as records are inserted, updated, or deleted. B plus tree index is automatically maintained in the database management system as insertion, deletion, and update, etc. However, frequent updates to large tables can cause fragmentation in the index. Regularly analyzing and reorganizing index to reduce fragmentation, whereas frequent updates on tables it causes fragmentation. Regularly we organize data, we reduce fragmentation, can keeping B plus T indexes in an optimal state. For instance, in SQL Server, you can use commands like alter index all on orders rebuilt. So it rebuilds all on orders table and reduce the fragmentation. It will performance tuning and analysis. Utilize explain statements to analyze how the dbms is executing your queries. The output of the explain statement helps you verify if the b plus t indexes are being used efficiently. Explain select star from orders where order date is equals to 2023-01, where explain statements helps you verify if the B plus T index are being used efficiently. Explain statement uses helps us to use B plus T index are used efficiently or not. Whereas if you find any certain query are not utilizing, if we find any queries which are not used by as expected, consider reevaluating your indexing strategy or adjusting your queries to leverage the B plus T more effectively. To work B plus T effectively, we also reevaluating our index strategy or adjusting our queries also. Where B plus Ts are widely used in the database management to optimize data retrieval, especially for indexing purpose. Where B plus Ts are used in dbms to optimize data retrieval, it is easily retrieve the data with the help of indexing values. The P plus T is a type of self-balanced tree that allows for efficient insertions and lookup operations. The primary goal of using B plus T in dbms is to keep the height of the tree low and maximize the number of keys. And in dbms we should reduce the height of the tree and we should maximize the number of keys that can stored in each node, which reduces the disk input output and optimizes access time. It helps to reduce disk input output and time management also. How B plus T is optimized? Balanced structure with minimum height, where B plus T maintains a balanced structure by ensuring that all leaf nodes are at same depth, whereas by considering a tree all the leaf nodes are at same depth, it should be balanced structure with minimum height. This balanced nature minimizes the height of the tree and keeping the search time in O of log n, where n is the number of keys, and it minimizes the searching time to search the data. Efficient range queries. Unlike B minus tree, B plus tree have all keys stored at the leaf level with linked leaf nodes. This allows for quick travels across multiple keys. Whereas in B plus trees have all keys stored at the leaf level. When all keys are stored in the leaf nodes are linked with leaf nodes, it is very easy to travel all the keys in a range queries. You can sequentially access data at the leaf node without re-navigating the internal structure of the tree. I fan out. B plus trees maximize the fan out number of pointers in internal nodes, which keeps the height of the tree low. This characteristic is particularly helpful because it reduces the number of disk access required to traverse the tree and find the desired key. Whereas we use high fan out, B plus to maximize the number of pointers in internal nodes. It can access it reduces the disk access to require or traverse the tree. Well, as some examples, balanced structure with a logarithmic depth example. Suppose you have a B plus tree with 1 lakh 10 lakhs records and a branching factor of 100. In a binary tree, the depth would be close to 20. In constant, the depth of B plus tree would be a depth of 3, means it takes at most 3 steps to reach any key, significantly reducing the such step. For example, you have a 10 lakh records and branching factor, whereas branching factor equals to height of left subtree minus height of right subtree, whereas branching factor is 100. In a normal binary tree, the depth would be 20, but in a B plus tree it would be 3. The depth of the 10 lakhs records should be 3, and it is very easy to search or reach any key, significantly it also reducing the search time. Separation of internal and leaf nodes examples. In a B plus tree, internal nodes hold only the keys needed for navigation. An internal node can hold 4 keys such as 10, 20, 30, 40, pointing to the following child nodes. Whereas internal nodes stores keys which are need for navigation to search for leaf nodes, whereas here we observe some tree which has 10, 20, 30, 40 all internal nodes, and if in each leaf node L1, L2, etc. actual records like 5, John or 15, Joe are stored in a level. In L1 record, we have stored some values 5, John or 15, Doe are stored. This structure means internal node can fit more, reducing tree height and traversal cost. It reduces the tree height and traversal cost also. Efficient range queries examples. Imagine you want to find all the records between 10 and 14. If you have to find records between 10 to 14 in a B plus 2, once you find the leaf node where 10 is node. While searching, we have to find 10 leaf node where it is stored, and you can sequentially link it, and you can sequentially search the linked leaf nodes to retrieve values between 10 to 40, that is 15, 20, 25, 30 and so on. This avoids the need for repeated searches for each values, and it reduces the search time also, and which is not needed for repeated searches to find values between 10 to 40. High fan out factor example. Consider a disk page size of 4 KB and key size of 4 bytes. If a node can fit around 1000 keys, this means each internal node have 1000 nodes. If around 1000 keys, each internal node has 1000 pointers. And B plus tree storing 1 billion fan out of 1000, the tree height would be about. This greatly reduces number of disks needed to find a key. And minimized disk access example. Let's say a database has 10 million keys stored in a B plus tree. We have 10 million keys that is stored in a B plus tree with branching factor 100. If each disk access loads an internal node with 100 keys, internal node have 100 keys. It only takes at most 3 disk reaches the leaf node. While we traversing to obtain leaf nodes, it would take only 3 disks. First read the root and then read the next level node containing 100 keys per child. Finally, they reach the leaf node or pointed to the data. Stored leaf nodes are sequentially access example. If you are retrieving all employee records with IDs between 100 to, you can find the leaf node starts with 100. While we have retrieved the employees records in an employees table between 100 and directly we go to 100 leaf nodes. Then since leaf nodes are linked with one another and efficiently we traverse from one leaf to the next, reading ID sequentially until 200 is reached. Efficient insertions and deletions example. When inserting a key like 25, the B plus T splits a full node it 2 nodes if necessary. For instance, if a leaf node already contains 20, 30, 40 and you insert 25, the node may split into 20, 25 and 30 and 30, 40, updating the parent node with pointers to these new nodes. This dynamic restructuring keeps tree balanced. When we have a node 20, 30, 40, by you inserting a 25, it will split the nodes 20, 25 and 30, 35. When we inserting a new element into 30, every time it's restructuring to balanced to obtain balanced trees. These examples illustrate the efficiency of B plus trees in different scenarios, especially with large scale data. Let me know if you'd like to go to deeper into any of these. B plus tree index files. B plus tree indices are an alternative to index sequential files. Disadvantage of indexed sequential performance degrades as file grows. Since may overflow, blocks get created. Periodic reorganization of entire file is required. Advantage of B plus T index files. Automatically reorganizes. It helps itself with small local changes in the phase of insertions and deletions. Reorganizing of entire file is not required to maintain performance. While we maintain the index files, uh, we are not reorganizing the entire file while maintaining performance, but we have disadvantage also. Periodic recognition of entire file is required, and since may overflow, block get created. Extra insertion and deletion overhead, space overhead. Whereas B plus 3, advantage of B plus 3 outweigh disadvantage, and they are used extensively. B plus 3 node structure, typical node where ki are the such key values, where pi are the pointers to children, where pi is the pointers to or keys to the non-leaf leaf nodes, or pointers to the records or buckets or records. The such keys in a node are ordered as k1 less than k2 less than k3 less than and so on less than k of n minus 1. Whereas B plus tree index file. A B plus tree is a rooted tree satisfying the following property. All paths from root to leaf are at the same length. Each node that is not a root or a leaf has between of n by 2 and n children. A leaf node has between n minus 1 by 2 and n minus 1 values. Special if root is not a leaf, it has at least 2 children. If the root is a leaf, that is there are no other nodes in the tree. It can have between 0 and n minus 1 values. Thank you.